Okay, welcome everybody back to physics. We're talking about centripetal motion, space elevator, force of gravity. We're going to step out the space elevator for now, which means we don't have to worry about having constant angular velocity. We're going to talk about the force of gravity equation. So the force sub g, or the force of gravity, is big G, which is 6.67 times 10 to the negative 11. And that's the gravitational constant, or the universal gravitational constant, they call it. And this is the fix-it number for the relationship that we're going to talk about here. And it works. It gets all the units and everything into the right, order of magnitude and stuff in order for them to fit into all the other equations. It's a fix-it number for the relationship. So M1, M2 could be any M1 and M2. So at this point, we will talk about the force of gravity between Brent and Mickey. Okay, so the mass of Brent is what in kilograms? 65, very good. 65 kilograms, just as a cross-country runner should be. And Mickey, your mass in kilograms? 50? Maybe? 50, we'll say, for fun. And how far away are you guys? You're 1 meter from each other. Okay, so that's what all these things are. 1 mass, 2 mass, the distance, well that's the square, but the distance between the two center of masses. Okay, so I need to see you guys put this in your calculator, and I'll get the same number, okay? So it sounds like the correct answer is 2.17 times 10 to the negative 7th newtons. Not real strong attraction due to gravity. Right? So it's not about the gravitational attraction. It's more about the chemical attraction, right? You have to talk to Ziegler about that. Okay. So let's see what the force of gravity is between Brent and Harrison.
Hey, buddy.
Sounds like you got something going on already. That's good. That was the force of, I don't know. Okay, so we got 65. Harrison, what's your mass? Let's just say 65 for the sake of argument here. Or no, let's say 50.
I'm good with that.
Really? You want to be that skinny, huh? Okay.
Great.
But the thing is, Harrison is 0.75 meters away versus 1 meter. So let's see what the force of attraction is between Brent and Harrison due to gravity. Okay, so everyone's getting this. So apparently, there's more attraction between Brent and Harrison because of this. Remember, the force of gravity is, according to the distance, is an inverse square law. So you can do this then, right? I mean, you can put these numbers in your calculator. Anyone else need help with that? Well, I got a question for you then. Let's say that we have an Earth here, okay? And we have a satellite. And let's say that my satellite can hit 6,000 meters per second, no more. The question is, can this orbit, and if so, where at? So keep in mind, my satellite is going to be moving around the Earth, right? And I'm saying the tangential velocity is constant. Is there still acceleration? Yes or no? Lauren? Very good. There is definitely acceleration. And the reason why that is because my tangential velocity is in straight line. Well, something has to fix that direction change, right? So there's centripetal acceleration, which means towards the center, or center seeking. If the tangential velocity is constant, then it's only changing angle. So I'm going to give you a new formula. Centripetal acceleration is tangential velocity squared over the radius, and the radius would be from the center of the rotation to the edge of the rotation. So it's really like the radius of the circle. with a circular path, okay? So, I've got a question then, Whitney. If there's centripetal acceleration, is there an unbalanced net force? Yes, very good. Because if we have an acceleration, Newton's second law says that we have to have a net force causing this acceleration. So, the formula for centripetal acceleration, real plain and simple, Nate, is
Tangential equals omega times.
very good. Mass times acceleration centripetal, just like all the formulas. Force equals mass times acceleration. Okay, so this is not hard. In order for you to get all the right answers, you have to write like this stuff down in simple form and get to the final formula that you're going to use without putting numbers in. Okay, so you'll see a pattern that I'm doing. I don't want you to write down the last formula necessarily to use. I want you to write it down so that you know when you get there with your algebra, you have the right answer. So if force centripetal is MAC, then force centripetal can also be, well, this is AC, A sub C, so it's mv squared over r. Okay, so in terms of velocity and distance from center of motion, force centripetal is mv squared over r. But the question then, Alex, is what m is this that we're talking about here? Which m is this? Is that the mass that's causing this force? Is it the mass of what's being forced upon by the mass causing the force? Which of course you can't have one without the other because of Newton's third law. But what mass is that? If we're talking satellites and the Earth, is that mass the satellite or the Earth? The satellite, very good, right? Because an unbalanced force causes a mass to accelerate, and we're talking about this acceleration towards the center, and that would be of the satellite. Or the thing that is going in centripetal motion. Now, we're going to take away this tether to the middle later on, but right now this is almost like a string holding this thing in motion, right? But the string just happens to be invisible, and it's the force of gravity. Okay, so let's see. We also defined then what is the force centripetal? Like the actual force centripetal that's causing this satellite to stay in motion is Grant. Gravity, correct. So the force of gravity is causing this force centripetal. Do you guys agree? Okay. Force of gravity is big G m over r squared, and that causes the mass of the satellite with a tangential velocity to stay an equidistant from the Earth. Okay? So the next question is, how do we go about and change this algebraically or simplify without putting in any numbers? Mickey, can I cancel out an m? Yes, right? But the question is, what m did I cancel out? The mass of the satellite. Very good. That's the m I canceled out. Okay. And then the next question, are these r's the same r? They are, right? Because here's the Earth. This is how far I am away, so I have a force of gravity on a satellite. And it also happens to be the radius of the centripetal motion. Okay, so I can cancel that out. And I can come up with, now really what I'm looking for here, my first initial question was, can I do this? But maybe the better question would have been, where would my satellite need to be as far as in terms of how far away from the center of the Earth do I need to be in order to have the centripetal motion, free centripetal motion, because of course gravity is the only real force acting on besides some small correction rockets. So I'm going to solve for r, okay? So gm over v squared, right? As long as I did my math right, this is how far away I would be from the center of the earth. So now let's just plug and chug, like they like to call it. So g is 6.67 times 10 to the negative 11. The mass of the earth is, anybody have it on their Google machine, in kilograms? 5.9722 times 10 to the 24th, and that's kilograms, right?
Yep.
Okay, I'll write that power so everyone can read it. 5.9722 times 10 to the 24th. That's more, moly cow, that's more than a mole. 6.02 times 10 to the 23rd, that was the biggest number in the world. I guess we have more kilograms than that. I wonder how many moles we have. Well, anyway, we have 6,000 for our meters per second, right? And then we can find out how far away do we need to be from the center of the earth. Put this into your calculators and see what you get. Okay, this is the initial number we're coming up with, 1.107 times 10 to the 7th. Do we agree with that? Okay, and that's meters. Okay, and the radius of the earth was, what's the actual radius of the earth? So this is outside the radius of the earth, so we can do this. This is real. Right? We can do this. But it's further than where we said than the speed we said we were gonna, it's further away. So like if this is the center of the earth, and we said this is low Earth orbit, then this is gonna be a step above that. Does that make sense? Okay. So that is an actual distance. We can actually orbit there with a velocity of 6,000 meters per second. So if we get further and further and further away, it would get, what, less and less or more and more? Less and less. So what's going to happen to our space elevator? Is it going to be slower than this? Slower. Does that agree with your lab findings and your constant, and, you know, I don't know if you came around to that part or not. But. Okay, so here, I got another question then for you, because I won't be here tomorrow. You're going to have an assignment. So we're going to untether the centripetal motion, and we're going to say there's a car, okay? And we'll say that it has a tangential velocity of 20 meters per second. We'll say that it's on a racetrack that has a radius of 10 meters. My question to you is, what's the coefficient of friction? Okay, you got a couple minutes. We'll say the car mass is 1,000 kilograms. Yes, that's perfect. That's the first line of your math algebra. The force centripetal is caused by the force of friction. Okay, so let's look at this together. Force centripetal is mv squared over r. And that equals the coefficient times the normal. So the coefficient is mv squared over rn. So the coefficient is 1,000 kilograms times 20 squared divided by 10 times 10,000. Did I put all my numbers in correctly? Okay, so what do we get for our final answer?
4.
Is it 4? So our coefficient of friction is 4, which is big, which it should be if it's a rubber tire, right? Because we're actually stopping that movement. Or we're not stopping it, we're changing the direction. Yes. Okay, so hopefully this helps you with some of the questions you might have on your assignment tomorrow. Have a good day.